Welcome to G Fun Facts Online. For decades, one battery has ruled them all. The lithium-ion battery powers our phones, our laptops, and the electric car revolution. But its reign is showing cracks. The materials it depends on, lithium, cobalt, nickel, are scarce, expensive, and often mined in geopolitically sensitive regions. This has sparked a global race for a successor, and a powerful contender is emerging, powered by an element you have in your kitchen right now: sodium. That's right, the same sodium found in table salt and seawater is at the heart of the next wave of battery technology. Major players like CATL, the world's largest battery maker, are already rolling out their first sodium-ion batteries for cars. This isn't a distant future technology, it's happening now. So today, we're diving deep into the physics, the promise, and the challenges of the sodium-ion battery. At its core, a sodium-ion battery works almost exactly like a lithium-ion one. It's all about an electrochemical dance. Imagine two electrodes, a positive cathode and a negative anode, separated by a barrier and bathed in a liquid called an electrolyte. When you charge the battery, you apply voltage, which forces sodium ions, that's Na+, to leave the cathode, travel through the electrolyte, and embed themselves in the anode for storage. When you use the battery to power something, the process reverses. The sodium ions spontaneously travel back to the cathode, and this movement forces electrons to flow through your device, creating an electric current. It's a simple, elegant shuttle service for charged particles. But here's the crucial difference that changes everything: the charge carrier itself. A sodium ion is significantly larger and heavier than a lithium ion. Its ionic radius is about 1.02 angstroms, while lithium's is just 0.76. This might sound like a tiny difference, but in the world of atomic engineering, it's a chasm. This size difference dictates what materials you can use, how the battery performs, and presents a unique set of engineering puzzles that scientists are racing to solve. The search for the perfect sodium-ion battery is really a story of materials science. It's a hunt for the ideal combination of cathode, anode, and electrolyte that can efficiently handle these larger sodium ions, delivering high energy, a long life, and top-notch safety. Let's start with the cathode, the heart of the battery. The cathode material largely determines how much energy the battery can store and how many times you can charge it. Researchers are focusing on three main classes. First, we have layered transition metal oxides. These have a layered crystal structure, like a stack of microscopic sheets, which allows sodium ions to slide in and out. They hold the promise of high energy density. For example, a material called P2-type sodium manganese oxide has shown capacities over 150 milliamp-hours per gram. The problem is, as the bulky sodium ions move in and out, they can cause these layers to shift and degrade, leading to the battery losing capacity over time. Researchers, like a team at Princeton University, are tackling this by doping the materials, sprinkling in other elements, to make the structure more stable and conductive. The second class is polyanionic compounds. Think of these as materials with a robust, three-dimensional scaffolding structure. This rigid framework, found in materials like sodium vanadium phosphate, provides an incredibly stable home for sodium ions. This stability translates to excellent safety and a very long cycle life. The trade-off has traditionally been lower energy density compared to the layered oxides. But that's changing. A recent breakthrough from the University of Houston has produced a new sodium vanadium phosphate material that delivers a higher voltage, boosting its energy density by over 15%. This makes them much more attractive for applications where safety and longevity are non-negotiable. Finally, there's a fascinating group called Prussian Blue analogues. These materials have a very open, cage-like structure that allows sodium ions to move in and out incredibly quickly. This means they can be charged and discharged at very high rates. Plus, They are relatively cheap and easy to synthesize. Some have shown theoretical capacities just as high as the layered oxides. The main hesitation is a potential safety issue. At very high temperatures, they could release toxic gases. So while promising, there's still work to be done to ensure they are completely safe under all conditions. Now let's move to the anode, the sodium ion's resting place during charging. Finding a good anode has been one of the biggest challenges. You see, the standard anode in almost all lithium-ion batteries is graphite. But graphite's tightly packed layers simply can't accommodate the larger sodium ions efficiently. It's like trying to park a truck in a space designed for a compact car. This forced a complete rethink. The most promising solution right now is a material called hard carbon. Unlike the neat, ordered layers of graphite, hard carbon is a disordered, messy material. Its structure is often described as a